Good morning, everyone. It's really a pleasure to be back here today, back at Stanford, where, as Carlos said, I spent my undergraduate career and had a wonderful time. It's very exciting to hear the developments in medicine that are being propelled by big data. And this morning, I'd like to broaden the discussion and talk about big data in other areas of science. The National Science Foundation supports research in all areas of engineering and science. And big data is changing how scientists perform their work and how future scientists are being educated. As Carlos just mentioned, I'm an astrophysicist by training, and in that community, we're no strangers to the concept of big data. The universe, after all, is a big place. We've been dealing with big science for many years, including big data sets, big simulations, and sometimes huge collaborations. The impact of this on our knowledge of the universe has been tremendous. And I know the potential impact of big data in biomedicine to improve healthcare and quality of life is also huge, as we've been listening to this morning. I think we all recognize the importance of big data for transforming science and benefiting society, but I'd like to say a few words about this. We're moving from the information age to the age of analytics, from the Industrial Revolution to the data revolution. Advances in our ability to store, integrate, and extract meaning and information from increasingly large-scale and diverse data sets are critical to accelerating the pace of discovery in every science and engineering discipline. From new insights about clinical decision-making to new ways to mitigate and respond to natural disasters, or to develop new strategies for effective learning and education, the impact and opportunities for data-driven discovery are remarkable. Big data also has the potential to solve some of the nation's most pressing challenges, not just in healthcare and medicine, but also in education, in energy, transportation, commerce, disaster prevention and mitigation, and cyber and national security. Indeed, in just about every facet of society, yielding enormous societal benefit and enhanced quality of life. I want to begin by illustrating the incredible power of data in telling you a story about the work of Daphne Koller, who's here at Stanford and has been involved in the big data movement before it was big. As you may know, Daphne, from her dedication to education, is the president of Coursera, an education platform that offers free courses online to people who want to learn, as well as to enable researchers to mine data on people learning. And you may know her from her leadership of the university's summer research experience for undergraduates in computer science program, which has trained more than 500 students. Or perhaps as the founder of Stanford's biomedical computation major. Not only has Daphne been an advocate for big data's potential for education and the science of learning, but she's also a leading computer scientist turned biologist. Daphne and a team of computer scientists and pathologists from Stanford developed a model to teach computers to analyze breast cancer. By measuring numerous novel morphological features of images of breast cancer tissue, the model can more accurately determine cancer diagnosis and prognosis than humans can. An astounding outcome of this work was that the cellular features that were the best predictors of patient survival were not from the cancer tissue itself, but rather from adjacent tissue, something that had gone undetected by pathologists and clinicians. Harnessing big data has the potential for a big impact in all areas of science and engineering, driving new innovations and addressing some of today's most pressing challenges, enhancing our quality of life. Now, let me take a few minutes to give you the big picture about NSF's role in the national and global science and engineering enterprise. The National Science Foundation, which I'll also refer to as NSF, is the only federal agency whose mission includes support for research across all the fields of science and engineering, of course, leaving most of biomedical science and engineering to NIH. but not all of it. Our mission is, quote, to promote the progress of science, to advance the national health, prosperity, and welfare, to secure the national defense. We engage the research community to develop new fundamental ideas, which are then evaluated by the best researchers through a robust peer review process. And that's a process widely emulated around the world. These ideas are evaluated on two criteria: intellectual merit and broader impacts. So here's NSF by the numbers. We operate with an annual budget of about $7.5 billion. We pride ourselves on being a lean agency in the administrative sense, with 94% of our budget returned to the nation to fund research and educational activities. We receive about 50,000 proposals each year, and through the merit review process, select about 11,000 of those proposals for funding. Funding support reaches about 2,000 institutions and 300,000 researchers annually. But you can do the math. It means there's about a 20% funding rate, which is low. So a lot of really excellent proposals get left on the cutting room floor. At NSF, we aren't only where discoveries begin, that's kind of our motto, but also where discoverers begin. And you heard from Carlos the example of funding the Stanford Digital Libraries project way back when Larry Page was a graduate student, and he took advantage of this program, collaborated with Sergey Brin, who had an NSF Graduate Research Fellowship, and the rest is history. NSF has a proud history of supporting our nation's best and brightest, whose research results have transformed our world, enabling a broad array of innovations, from technologies in our mobile devices like GPS and 4G, the Google search engine, and even the internet itself, to MRIs, novel drugs for medicine, the bounty and safety of our food supply, the discovery of the Higgs boson, and the invention of 3D printing. We're proud to say that 214 Nobel Prize winners, one of them just from last year's group here at Stanford, and thousands of other trailblazers have transformed our understanding and our world with NSF funding. In July, we mark the 75th anniversary of the establishment, the 65th anniversary of the establishment of NSF. The vision for NSF was, in large part, laid out in the report of Vannevar Bush. The report was titled Science, the Endless Frontier. It was commissioned by then President Franklin Roosevelt near the end of the Second World War. The vision was to build a strong foundation of knowledge upon which innovation can thrive through support of basic or fundamental research. And the other part of that vision was enabling funding for the next generation of scientists and engineers. In addition to being committed to fundamental research, we also ensured that we adapt to changes that have occurred in the last 65 years, and big data is an example of such an area. Data are motivating a profound transformation in the culture and conduct of scientific research. To harness the potential of data, NSF has been a leader in helping to coordinate data science research and development activities across the federal government and across the nation. In the spring of 2011, the White House stood up an interagency group with NSF and NIH as the co-chairs, and with members from 16 other federal agencies. And in case you don't recognize them, that's our John Holdren, the President's science advisor, who initiated that. A year later, NSF provided leadership for the launch of the National Big Data Research and Development Initiative. Most of the member agencies made commitments to invest in big data research and development, with investments totaling more than $200 million that year. The cornerstone of these announcements was a joint research program between NSF and NIH. And in November 2013, responding to President Obama's call for all hands on deck and ensuring that the Big Data Initiative is not just for federal agencies, but also a national effort, more broadly construed. NSF again provided leadership in an event announcing 30 multi-stakeholder partnerships with 90 partners committed to work together to move data to knowledge to action. While interest in data science has risen exponentially over the past several years, NSF has been investing in data science for several decades, well ahead of the curve. NSF has a bold, comprehensive 5-part approach for this increasingly data-centric world. And this diagram illustrates those 5 parts. First, we support fundamental research, sometimes called basic research, discovery research, curiosity-driven research, to scale collection, management, storage, and analysis of data. Second, NSF invests in research infrastructure at national and international levels to support and serve our research and education community's needs for data-intensive science and engineering. Third, NSF supports education and workforce development to improve the nation's capacity in data science. Fourth, NSF enables community building, collaborations, and partnerships to support interdisciplinary science and to accelerate the transition of research into practice. And lastly, policy plays an important enabling role as it enables broad dissemination and sharing of data, software, and knowledge. So I want to take a few minutes to elaborate on each of these areas. Oops, wrong direction. Here we go. NSF investments in fundamental research and data science help to develop and prototype new techniques and technologies to derive knowledge from data. This research aims to advance the core scientific and technological means of managing, analyzing, visualizing, and extracting useful information from big data sets. It includes facilitating the development of new data analytic techniques and algorithms, scalable, accessible, and sustainable data tools, and large-scale integrated statistical modeling. I've already told you about Daphne's method to analyze images of breast cancer. Let me also provide an example that focuses on data tools by telling you about Matej Zaharia, who is the latest recipient of the ACM Doctoral Dissertation Award. In his graduate work, he developed a new, resilient way to perform computations on a cluster of computers that matches or exceeds the performance of specialized systems for many applications. In October 2012, just 6 months after the launch of the National Big Data R&D Initiative, NSF and NIH announced nearly $15 million in new big data fundamental research projects. By the end of this fiscal year, this program will have invested nearly $80 million in critical techniques and technologies for big data. Another pillar in NSF's strategy for data science is supporting cyber infrastructure to manage, curate, and serve data to research communities. For nearly 4 decades, NSF has supported advanced computing infrastructure for the nation's research and education communities. While this began initially as support for supercomputer centers, an effort that has been tremendously successful, we're now planning for a future that embraces both high-performance computing as well as data-intensive computing. To illustrate the range and scope of some of today's cutting-edge and computationally intensive cyber infrastructure supported by NSF, I want to give you just a couple of examples. In astronomy, the Sloan Digital Sky Survey collected more data in its first few weeks of operation than had been amassed in the entire previous history of astronomy. And the Large Synoptic Survey Telescope, called LSST, which is being built in Chile and due in about 2020 to be built, will have the ability to amass double the quantity of data that the Sloan Digital Sky Survey collects in a decade in just 1 week. In ecology, NEON, the National Ecological Observing Network, is a continental scale research instrument. It has about 106 sites. It integrates sensor networks, biological assessments, including natural history archival information, and remote sensing data. and it's really poised to revolutionize our understanding of the natural world around us. And the proposed National Brain Observatory would help neuroscientists collect, standardize, manage, and analyze the large amounts of data that will result from research attempting to understand how the brain functions. As a testament to the potential of a tool like this, let me show you an NSF video featuring neuroscientists here at Stanford, led by Russell Poldrack, who have launched new infrastructure to enable fMRI data to be shared easily and securely in a standardized format.
This one is sort of interesting. This is a study of dental pain.
These images illustrate how cognitive neuroscientists like Russ Poldrack are trying to read minds, so to speak.
Okay, we're ready to get started with the scanning.
They are generated by an fMRI, or functional MRI scan. Researchers use them to watch how blood flows through active areas of the brain in real time.
And we can use functional MRI not just to see how different brain areas turn on, but also how different ones move together over time. And that's how we know that we say that they're functionally connected, which means basically that they're talking to one another over time.
The fMRI is one of the most powerful tools available to image human brain function, but they're expensive. And right now there is only limited infrastructure for sharing results.
This is somebody reading words.
With support from the National Science Foundation, Poldrack and a team at Stanford University want to change that with a project called Open fMRI. They're working to make these dynamic brain scans widely available in a computer database to scientists all over the world.
The overall purpose of Open fMRI is to give people a framework to share their data.
Sharing fMRI scans is difficult because the data sets are large and cumbersome. Poldrack and company have standardized their format so they can be easily and securely uploaded to the Open fMRI database.
So our lab studies cognitive and brain development, both typical development as well as children with ADHD and autism.
Neuroscientist Vinod Menon is using Open fMRI to validate his own research. He says the more scans he can analyze, the more certain he can be of his conclusions.
They give us more confidence that these findings are strong and robust, and therefore they are worthy of further study.
And as more studies are added to the library, he sees it as a powerful tool for diagnosing and treating neurological disorders.
We'd be able to say how confident are we that this child might have autism based on some features of their brain imaging data. And I think we'll see a lot of progress in this area in the next 5 years.
You really have to bring together lots of data in order to be able to answer these questions. The willingness of researchers in the field to share their data seems to be really increasing.
Poldrack expects the shared database eventually will provide a comprehensive map for scientists to navigate the complex landscape of the brain. It's all about, well, putting their heads together on it. For Science Nation, I'm Miles O'Brien.
All right, thank you, Miles. So this is the kind of thing, of course, as you can imagine, that Congress really likes to see, and maybe we'll get to it in the Q&A, but I think our Understanding the Brain initiative, which we do in collaboration with NIH, is well, I don't just think I know, it's very, very popular and has a lot of support by Congress. So now I want to talk about our investments in big data research and infrastructure in the area of education and workforce development. We really aim to improve not just the amount and kinds of research we do, but also to continue to invest in the development of human capital. A 2011 McKinsey report predicted, quote, by 2018, the United States alone faces a shortage of 140,000 to 190,000 people with analytical expertise and 1.5 million managers and analysts with the skills to understand and make decisions based on the analysis of big data. In this era of big data, where data analytics is a core skill, we have to strive to train what are increasingly being called Pi people, a term coined by Alex Saleh of Johns Hopkins University. Pi people represent individuals with a pillar of knowledge in their own field and a second pillar in the ability to execute the statistical and computational methods that drive modern data-intensive research connected with interdisciplinary science and engineering. And increasingly, as I go around to universities, I see presidents and chancellors investing in curricula that actually can develop both the content and the data analysis tools simultaneously in our undergraduates as well as graduate students. In order to ensure that graduate students develop the skills, knowledge, and competencies needed to pursue a range of STEM careers, NSF launched the NSF Research Traineeship Program and singled out data-enabled science and engineering as the priority research theme for its first 2 years. So that's a new program in funding graduate students. As you know, you all are probably beneficiaries of the graduate research assistantships, which have been so valuable for decades, and also some of you of the graduate research fellowships, a smaller but very, very distinctive group of individuals who receive those. Well, our latest is this NSF Research Traineeship program, and that is focused on areas that we think the country really needs investment in, and our first theme is data-enabled science and engineering. Nurturing interdisciplinary science communities and meaningful collaborations is an important fourth part of NSF's strategy for addressing big data. It's also an essential component in realizing the full power and the benefits of big data approaches, whether in science, business, government, or other societal impact areas. NSF is seeking to enable research communities to develop new visions and teams and capabilities to accelerate discovery across all areas of science and engineering, as well as to accelerate the transition of discoveries into practice. And so we put a lot of money recently into making the engine of translation a little faster, more efficient. By promoting strong connections between academia and industry, NSF further enhances its research portfolio in big data with fundamental concepts and new ideas that are directly relevant to the commercial sector. NSF is currently in the process of establishing a national network of big data regional innovation hubs. The vision is to form connected, multi-stakeholder regional consortiums with members from academia, industry, government, and the nonprofit sector to facilitate the transformation of data to knowledge to action, while also creating and maintaining an agile and sustainable national big data innovation ecosystem. A final important component of the data strategy at NSF is our policy framework that enables dissemination and sharing of data and knowledge. Earlier this year, in mid-March, NSF released its public access plan, in which NSF recognizes the uniqueness of the broad community it supports. The plan is an open, flexible, and incremental approach to providing access to publications, data, and other products of NSF funding. I think some of you are very used to the PubMed form. That is not the perfect fit for all the different disciplines of science and engineering that NSF funds. So we have a more flexible, diverse approach, let's call it, utilizing DOE facilities and wherewithal. I encourage you to see NSF 15-52 online if you're interested in more details about our open access publication plan. And our next step is to go to an open access data plan. Recognizing that data sharing is important not just within our country, but also across the globe, let me also point out that we fund the US participation in an international organization called the Research Data Alliance, which aims to accelerate research data sharing among scientists around the world. This alliance is working to tackle data sharing challenges such as interoperability, stewardship, sustainability, and use. We've seen powerful examples in the past few years where open and shared data have enabled profound scientific discoveries. In fact, sharing information and data is at the heart of public participation in scientific research, or crowdsourcing. And I know you closed your previous discussion this morning with some talk about crowdsourcing. Consider the game Folded, an effort led by researchers at University of Washington and funded by NSF, which enable players across the world to map the structure of a protein that has the potential to help fight the HIV and AIDS viruses, a problem that had stumped scientists for over a decade. And it was done in just 10 days. Together, advances in these 5 areas are essential for accelerating discovery across all areas of science and engineering, enhancing innovation, driving societal benefit, and improving our quality of life. Before I conclude, let me leave you with one more example, but instead of talking about big data, I want to focus on small data. I want to tell you about Deborah Estrin, a computer scientist who has, through a series of events, been compelled to focus her efforts on mobile health and small data. Deborah believes that using an individual's mobile device to capture data and serve them back to an individual can have profound implications for healthcare. Just 2 weeks before her father passed away, his behaviors radically changed. He stopped walking around the neighborhood, going to the grocery store, responding to email. For any healthcare professional who didn't know him, they might not think that any of these behaviors were unusual for a 90-year-old. But for Deborah's father, they were a signal that something was wrong. A mobile phone easily monitors each of these activities, but a platform that serves this information back to an individual or enables that person to share the data with family or caregivers wasn't so easy. In order to change that, Deborah has co-founded a startup company called OpenM Health to transform the way personal digital data can be used in healthcare. You heard from one of OpenM Health's other co-founders, Ida Sim, yesterday. The potential for data, both big and small, to transform healthcare is just tremendous. As the stories I've told illustrate, data science will help to enable healthcare that is more evidence-based, personalized, and proactive. NSF is helping to make this vision a reality through its support of fundamental research to understand data infrastructure and give the support to science and education communities, education to meet the momentum of this data-centric world, collaborations and partnerships to support interdisciplinary science and accelerate innovation, and policy to enable dissemination and sharing of data. Harnessing the power of data will not only shape delivery of healthcare, but also will improve our overall quality of life for decades to come. That's our mission, and I know it's yours. Thank you very much.